So hello back, everyone. So we're here for the last session of the week on Python GPU, and this session will be dedicated to PyTorch. Okay, so there will be two parts: a general presentation of the PyTorch library, and afterwards some exercises or 3 or 4 different notebooks on PyTorch tensors, derivation, autograd, and after the exercise for Gray Scott equation solving with PyTorch library. Okay, so we will start with a quick presentation. So just a question to the audience before I start: who already used PyTorch library? Okay, so 4 people. Okay, so not that much. Okay, for what purpose? Deep learning or deep learning? Okay, mainly. All right, so let's go. Let's start. So PyTorch, we classed it as an intermediate library compared to JAX or the others. Why? Because you can do some low-level computing on tensors with it, but you can also do some high-level computing with equation and this kind of stuff. So this library has been created by Meta, formerly Facebook, on the impulse and initiation of Ian LeCun. It's very useful for large language models. So 2 famous models developed on PyTorch are OpenAI's GPT, for example, and DeepSeek, which has been lately released. Okay, so if you open up the notebook for training for DeepSeek, you will see that it has been used. PyTorch are also some of the subsidiaries libraries like PyTorch Lightning. For the deep learning. So it's mainly done for deep learning, but the purpose today is to use it for tensor or matrix computation. Okay. So it combines a lot of several functions, arithmetic operation for tensors, but not the NumPy model. So here you have to pay attention to the difference that we said yesterday between a tensor and a matrix. Okay, a matrix in the general language is maximum 3 dimensions. Tensors can go over that, and that's where the separation. So tensor is more a keyword in deep learning community, let's say. Okay, it's also dedicated much to deep learning operations for neural networks and graphs, and for the deep learning purposes, it has also some very powerful derivation operation with the autograd for tensors, and also for analytical functions. We will see that also. Okay, it's if you summarize a little bit, it's very close to JAX, but not that powerful as JAX. Okay, so we have a summary at the end of the session of a comparative between the two on all the other libraries we saw today. So the installation is quite easy. Import Torch, and you get it on your computer. So if you need the others libraries like Torch Vision, Lightning, you have to import them also independently. So what is the backend of PyTorch? So there is many backends, CPU, CUDA, CUDA-den, MHA, a lot of them, even Xeon, okay, which is not very useful, but still it supports a lot of backends. It's based on cuBLAS library, actually, for all this. The integration of cuTLAS is underway, but it's not finished yet. It's an undergoing work right now. With the general matrix multiplication library integration. So this has been done, work ongoing for 2 years now, but it's still under its way. And for the recent events, there is the integration of OpenXLA for TPUs use. So TPUs are typically processors that you find in Google Cloud. For nowadays, only TensorFlow use TPUs, but PyTorch is also working on making implementation on TPUs to get faster processing actually for matrix calculation and deep learning. Okay, so for this, for the backends, you can find the list for the stable version of CUDA on the link right below. So it's a very dynamic library, and considering the hype on the AI right now, actually it's still evolving much. Tensors, okay. So you have 2 ways to make tensors for PyTorch. You can install them, make a tensor or a variable, let's say, on a CPU directly. So by default, when you declare a tensor, it will be on the CPU, okay? You can, once it's done, actually you can move your tensor between the CPU and GPU very flawlessly. So this is what we're gonna see later. But first, to see if you can do that, you have to check if you have a GPU available. So there is a command for this. You see the CUDA is available, and if it says true, that means that you have a GPU detected, okay? And you can even get the device name to see what model you have, etc. So all this we will see in the notebook later on to see really how to make sure that you have access to GPU that is detected by your Python script. The choice of allocation, so you can do it at the creation, or you can move it later. So you can create a tensor float directly on CUDA, okay? So CUDA 0 has a meaning, because GPU has a specification, it can handle many GPUs, okay? So when you list your GPUs, actually, PyTorch will assign a number to them, okay? Why this is done natively in the library? Because when you do some deep learning, actually, you need to split your data sometimes on multiple GPUs. And this is why it's done natively in the library. So you won't have CUDA without anything behind it. You have CUDA with a number, and that's the number of the GPU, the ones you want to send your variable, okay? So this is the way to do it. And actually, you can check where is your variable by ape.device. It gives you the where is your variable. You can check also the allocated memory by this command, CUDA memory allocated. And you can also move on the fly variables from GPU to GPU directly. So tensor 2 CUDA 0, you can move it tensor 2 CUDA 1, and you can switch your variable between your GPUs and the CPU on the fly, okay? The creation of a variable on the CPU and GPU, we will see there is the use of the command to, or just creation on the GPU. There is a subtlety for that, actually, because the to command here, tensor 2 command, offer you more flexibility, actually, when you move it. You can change the variable type just at the assignation to the GPU, okay? So we'll see an example in the notebook for that later on. All the arithmetic and matrix functions are available on the model of NumPy, actually, so exactly the same. View and reshape also are available. We will see an example of that, especially for the view, because it's very important for tensors, actually. Just to understand what are the dimensions of the tensor you're working on, actually, sometimes you have to, without modifying the tensor, to view it in another shape. You can do a lot of the matrix product and the element-wise multiplication also. And you can do also the broadcasting on the model of NumPy. So the broadcasting is not exactly the same than NumPy, actually. It works. You can have some bugs for that. So to use with parsimony and PyTorch. Till now, I still have some issues sometimes when I do some broadcasting on PyTorch site. Sometimes I prefer to do it on NumPy and to reconvert the tensor afterwards. Vectorizing functions. So we spoke in the introduction, I said something about the functions and the derivations. So you have on-the-fly function vectorization, and you have also on-the-fly function derivation that are available in PyTorch. So let's, for example, here we define a polynomial of the fourth degree, y function of x, okay? And we can, by using the autograd, actually compute the derivation of y at a certain value of x directly. So this works for analytical functions, but it also works for tensors, for matrices, or whatever you want. You can derivate anything you want, actually, with PyTorch. So analytical function, but also numerical functions. It's not dedicated only to analytical function. This is a very powerful function. It's mainly used in deep learning, of course, when you calculate your loss and you want to derivate your loss compared to the weights. So it can handle a lot of capabilities and overpowers. So we won't use it today on the Gray-Scott equation, but one solution would be actually to calculate the Laplacian with the autograd function directly. I didn't do it. It's a good exercise. But it should be faster because you parallelize everything with it. But see, there is a solution. Okay, so if you want to perform a derivation, actually you have to declare that you require grad as true. Okay, if you don't do this at the declaration of your tensor, you will not be able to make the grad computing, the derivation computing. So another example here with composite functions. Okay, so we create a tensor. Okay, x. We define y function of x. Then we define z function of y. So z depends of x, but we didn't say it actually. And after we calculate directly, we define the gradient as true, as I said. And after we can calculate the z derivation compared to x directly. So the library will do it automatically. You don't have to make the composite derivation by hand. So you don't have to compute the derivation of z compared to y and then the y compared to x. Okay, the library make it automatically. So here we kept z as a tensor, but you can also say I can define a norm on z, so transform it on a scalar, and there you guess it's about deep learning. So when you do some deep learning, you have to define a sum or a mean or a distance and or your weights. Actually, you have to derivate them afterwards, and this is why this function is useful. Actually, that's why it is easy in PyTorch to do composite, what we call composite derivation automatically on the fly. Okay, you can also, there is a library which called magnum.np, which is quite recent. I think it's 2024, that allows you to make finite difference, what we're doing in grayscale, directly on PyTorch. So it's a library that is derived from PyTorch and uses the power of PyTorch actually for make space differentiation on the fly. Okay, so you have the article here if you want to see that more closely. So we will see an example later on the notebooks en fait, on this topic. The profiling, so you have many ways to profile. So you can use the torch profiler. So in the notebook, I will show you an example of this. But you can also use the profiler that are included in Collapse, for example. I didn't succeed to make it work, or any other profiler that allows you actually to make profiling on GPUs. Nsight, for example, works very well with PyTorch. Okay. Another opening, so to follow, this is an example I found on NVIDIA website where they use PyTorch to make grayscale equation by deep learning on GPUs. Okay. So if you want to go further and see how you can do it without solving the Laplacian automatically, so the technique here is called PINs, so physics-informed neural networks. The word is here. Okay, so when you make some learning on the equation itself, and after you can solve it very quickly. And the advantage here is you can make it on the 3D space, not on the 2D space, and go very fast. Okay, there is also some other alternative to get PyTorch go faster, actually. You have the PyTorch JIT. I didn't use it myself, but it's worth to notice. So it's a model of just-in-time compilation like we saw yesterday on Julia, for example, or NumPy. And, sorry. And you can have also the usage of PyTorch Lightning for multiple GPUs. So this is specific for large models. A quick compare before the notebooks. I can say this, Alice, or no? Yeah. Yeah. So just to compare all the libraries that you say before doing the exercises. We can do it right now. So today you had CuPy, CuPy numeric, you had JAX and CuPy. And now you have to PyTorch. So the only library that fills all the items, including the multi-accelerators and the derivations, is JAX, actually. So JAX is the most complete one. It's maybe also a little bit complex, but voilà. For PyTorch, if you want to use multi-accelerators, you have to use subsidiary libraries like PyTorch Lightning or others.
What do you mean? Multi-GPUs you can use?
You can use, no, but if you want to use some IRM, for example, yeah. if you want to use TPUs, it's not used yet. Okay, so when I say other accelerators, I mean others than GPUs. Okay? Other than GPUs. Okay, and now we can go to the notebooks. So So as you see in my screen here, if you go to the repo that Alice and Jean-Marc did, you have a directory named GPU, and inside you have tutorials, and inside you will find 2 or 3 PyTorch, no, more than that, actually. You have PyTorch tensor operations, you have PyTorch gradients, I give them in the order, you have PyTorch conf2d final exercise. So this is the exercise we will do together, actually, to see how to solve the gray Scott equation today. And you have the one with actually the solution here. Okay, so this is the exercise and this is the solution. So for you, if you want to see the solution directly, it's fine for me. But if you want to do the exercise, open up this one, actually. Okay. You have also the Python script version, okay, that Jean-Marc did and included on the repo here in solutions. You can work on this one also. This one is more optimized for the HDFS and for the file writing, actually. So this is not what I'm doing on my notebook, but for the Python script, actually, is done on the HDF5 format file for generating the images and generating the video. So if you want, you go directly to the script if you want to write that one. But it's included with the all other solutions like JAX, key numerics, CuPy, etc. So this is PyTorch solution.py. So the script I just told you about. Okay, and this is the benchmark that Alice and Jean-Marc did about all the libraries, that you see that PyTorch is not far away from CuPy and the others, but we have still room for optimization if you want. Okay, so let's start with the first notebook, which is the tensors. Okay, so you can load it in your Jupyter notebook, but make sure that you have access to a GPU. Or you can do it, actually, import it in your Colab's Google Drive, and you open in your Colab, and it's free of charge for now. Okay, so I just put full screen. Everybody sees, or I have to zoom a little bit? It's okay? Okay. So let's go for tensor operations. So we can make some indexing and slicing, reshaping the tensors, arithmetics, dot products, matrix multiplication, addition, and more. So attention, when PyTorch is initialized with float 32, okay? So if you want to make float 64 for more precision, you have to set up this variable here to make it natively create tensors by float 64. So this can make you create some issues if you go from NumPy to Torch and vice versa, okay? So by default, PyTorch will create float 32 floats, okay? So first we have to import the libraries we're needing for this notebook. Here we are creating a tensor of 6 elements, and we shape it for 3 rows with 2 columns. Up. Very easy. So this is really at the model of NumPy for the newcomers. So it's very easy. You can grab the right-hand column just by the 2 points here. Up. And you can do the other way, actually, by slice. Up. So reshape and view. So these are copies of what you saw in NumPy before. So we can rearrange a tensor without changing it. So the view, actually, here I will create it. So I can take this tensor and view it in this shape: 2 rows, 5 columns. Okay, but it doesn't change the initial variable. So here's the proof. So we can view it in the other way. Up. 2, 5, 2, 2, 5. And here we check that x is unchanged, because if you plot only x, actually it saves the tensor that you defined before. So viewing is really useful, actually, if you want to really understand what is in your tensor or in matrix, actually. So it's not useful for computation. It's really useful to visualize the data the way you want it to appear, to understand a little more. Okay, so here we do some, so we will need the Z definition here later on, okay? So by passing -1 in the view option, actually, you will infer the correct form of the given tensor. So if you do this, actually, you see that it's the same thing. So, and you can change the -1 position. It doesn't matter, actually. So you have another option, which is very nice. If you have a lot of tensors and you want to visualize them the same way, you have the method view as. So we define the tensor here, which is z, which is a view of x, 2 columns, 2 rows, 5 columns. So we just say actually view x as z, okay? And PyTorch will automatically reshape x like generate a view of x like it is in z. So if you want to compare two tensors, okay, you can view them in the same view, let's say, without having to matter what are the dimensions, what are the columns, what are the number of lines, or whatever. So this is very useful, actually. Up. So now we go through tensor arithmetics. So here we define two tensors. So by default, as I said, it's created on the CPU. Okay. I don't know what machine I have here. So we have a T4. So we are on the GPU. We have a GPU machine available here. Okay. But in this case, I didn't say anything. So the tensor is created on the CPU. Okay. So if we add the two, actually, so it's added column by column. So A plus B, standard right now. You can write this another way. So torch add A and B. This is another way to do it. Okay. And you can pass it also as an argument. So you can pass the result as an argument. You can say add AB and output. You normally output as a result, and you print result, and you have it also. So there's many ways actually to work with tensors. It also depends on the way you want to do it. You can also change the tensor in place. So this is very straightforward. For now, all these operations are available. You have also all the transformation, absolute, square, square root, etc. All the sign functions. So this is I don't spend some time on this, but it's the same thing than NumPy. So here we will try to use it to do some operations. So this is here we make an addition of two tensors, but we sum them in the same way. Okay, so we have two tensors, 1, 2, 3, 4, 5, 6. We make the sum. We add them row by row. Okay, and you make the sum at the end, and at the result you get one tensor, which is one value actually. So this is very useful if you want to see what are the sum, not the mean, the sum of a whole tensor. Okay. But there is some other functions when you get the mean directly or a specified distance. We will see that later on at the bottom of the notebook. So you have also the dot products here. So very straightforward also. So you have to make attention that the matrix size corresponds for the dot product, of course. Okay. So here I did it in CuDA for fun. Okay, so I declared my tensor directly on the CuDA device, on the GPU. Okay, so when I do this, the multiplication is done on the GPU, of course. Okay, so if I have a variable on the CPU and a variable on the GPU, I will have an error if I do this. Okay, so you have the matrix multiplication also that is available. So this is also straightforward. I think you saw it in NumPy already. Up. We go fastly through this. So all this is done actually. So there is many ways: MM, A and B, M dot MMB. Yes.
When you call the CuDA function
here, yes,
because it's straight to the NVIDIA device.
Yes, NVIDIA device. CuDA is for NVIDIA.
Because Metal is also supported for PyTorch. And is it the same thing to do with point
I don't
device?
know.
And
I don't know. I never used Metal. I never
but
used Mac.
is CuDA, this
Yeah.
function, the same thing as putting device and under
Yeah,
between
but
parentheses put CuDA
can you have in
string?
Metal? Can you have the option to enumerate your GPUs or no? Because
I can put a point device and
it
between
works.
in theory. I will test it.
Yeah,
But
good.
I just wanted to know if it's the same thing as device and between parentheses CuDA in string.
Yes, it
Okay.
is. It is.
It's
Yes.
just a shortcut.
Yeah, yeah. So yeah, good test. But I don't know how these GPUs are numbered on Mac computers. Actually, it's a good question. Now, somebody has an idea about this or no? In the audience? Yes, go ahead.
I am trying to use NPS right now, I think, and you can select a device and then you can say to device instead of a number slot. I think I'm testing it now.
Okay.
It's working with device and NPS.
Okay. All right. Interesting. But let's stay on GPUs. There is a lot of people using Mac in the community here, or no? 1, 2, 3. Okay, you're really very small minority, huh? Sorry? Okay. 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 Don't worry. No judgment. No judgment. No judgment. Okay. Let's keep going. So for the matrix multiplication, actually, it's also straightforward. It's exactly the same thing that you have in NumPy with small variations. So you will not get problem for doing this. So now we have an example of broadcasting. So for this, I really encourage you to see the documentation of PyTorch broadcasting, but also on NumPy broadcasting, because they don't do the same thing. So broadcasting is done actually if you want to add or sum two matrices or two tensors that have not the same dimensions, and it's the way to complete them actually, so to make the addition or the arithmetic operation possible. Okay. So here we take two tensors randomly, 2, 3, 4 dimensions and 4 dimensions actually, and we make the multiplication of the two tensors, and PyTorch completes actually the second one, which is had a smaller dimension than the other one actually automatically, and makes the multiplication. So it doesn't work all the time. I agree with people that use it and had some bugs. But really, for broadcasting, you have to see the documentation to see what is possible to do with broadcasting or no. And here, actually, if I don't take the good dimensions, actually, I have an error. So, okay. So as I said before, we saw the sum actually. So there is a more interesting definition or a way to evaluate the value of variables than sum. Is the what we call the norms or the Euclidean norm. So this is integrated directly in PyTorch. You just define a tensor actually, and you type x norm, and you get the norm of the tensor. So it will, whatever the number of columns, the dimensions, the rows, etc. Actually, it will sum all the elements and give you actually the norm. If you want to see the number of elements, it's also possible with the method numel. You got it here. Actually, it will take all the elements of the tensor and give you actually an integer that gives you that. So allows you to make your own, let's say, norm, because here we define the Euclidean norm, but it's not the only used one to make for deep learning, for example. There is a lot of other norms. So defining norms allows you to compute your error and to calculate the derivation of the norm compared to weights. So this is why this function is integrated directly and computed also on the GPU, of course. So this is, I forgot to mention this. You can make this computing on the CPU and on the GPU the same way. Okay, so this was a brief introduction to tensors on PyTorch. So just a matter of language, tensors are just matrices that are bigger than dimension 3. Okay. And by definition, if you go more than 3 dimensions, it's very hard to visualize. That's why you have all these tools actually to try to understand what is in your tensor. So it's specifically done actually to work and to manipulate data for deep learning. Okay. So we go through the second notebook that you have on the repo, which one for the derivation. So I just will connect my machine here. So I just disconnect the other one. Up. So I just wait a few seconds for the machine to connect. So by the way, just an information, if you use Colab, actually use it in the morning because you have the time decay with the US. So if you use it at 4 p.m. at the US, actually, the access to free GPUs is a little harder because starting time on the GPS is 4 p.m. in France or in Europe. So by experience, in the morning in France, you have more access to GPUs in the free mode on Collabs than in the afternoon. Okay. Just for information, so if people get cut very quickly on your GPUs if you're using the free account on Collab, there is why, because the US they're starting their journey actually. So torch gradients. So the autograd function is hardly implemented in PyTorch, and actually this is used actually to make derivation, open time variables or space variables or tensors or analytical function, like I said. So this is done for calculating error functions for function transfer and neural networks mainly, but also for chorus sampling, back propagation, etc. So it's one of the backbones you have in PyTorch, actually, this ability to make derivatives on the fly. So you have a note on it here that is on the link, PyTorch autograd mechanics, to understand how it works. So, but the main use here is to compute the error functions, to derive the error function on the loss function in deep learning compared to the weights. Okay, this is one of the main use we have of it today. So I pass all the text here. So we start with defining the polynomial I show you in the example, y depending on x here. So we know the derivative of this, but we don't have to compute it because the library will do it automatically. So I import the library. I defined x as a tensor, and I don't forget to put the requires grad equal true. Okay, so I'm able to make the gradient calculation. And after I define y compared to x, okay? So this is, let's say, a flawless definition of the function, okay? Very easy, you just define, you write it this way, y function of x, okay? So it is well defined, no problem. So now if you want to calculate the derivative of y at x equal 2, okay? So here we defined it, okay? We click play, backward, print x grad, okay? And actually the value is 93, okay? So I didn't calculate the derivative. I just said calculate the derivative of y compared to x at the value x equal 2, okay? But we didn't go through the process of calculating the derivative ourselves, okay? So this is very time saving, okay? And next step, actually, we have the backpropagation on multiple steps, so on composite functions. So we will do the same thing, but we will vectorize a little bit our tensor to make it a little harder, actually. So we define another function y of x, 3 multiplied x plus 2, okay? And we defined another function, which is z, okay, which is 2 multiplied by y squared, okay? So this is composite. If you want to calculate the derivation of z compared to x, you have to, normally you should make all the composite derivation by hand. But there you don't, in this case, you don't have to do that. So you just, and yeah, more complex, actually. I transform my z function here. It was, until now, z is a tensor with 2 rows, 3 columns, okay? Here, I transform my z actually to a scalar, okay? So I use the mean function that is defined in PyTorch. So I will calculate the mean of the tensor, okay? So actually, you don't have 2 composite functions here. You have only really 3 composite functions, okay? Y compared to x, z compared to y, and the mean of z, okay? And what we do here, actually, so I don't forget to validate myself. Up. So if you want to make the hand computing, you have to do all this. Okay, we won't do it. It's just to show how hard it is if you have to do it by hand. Okay, so what we do here, we calculate the derivative of the output, the mean of z compared to x. Okay, and this is done here. Okay. Okay, so this is all the calculation you have avoided by using the autograd function. Okay, so it's very useful, especially if you have many composite derivatives to do. Okay, so I didn't do it for this class, but you can use the autograd instead of the Laplacian if you want to calculate the derivatives compared to the space, which is the U and V spaces, actually the U and V tensors of the Gray-Scott equation. So this is a possibility. Okay. So I hope this gave you an oversight of what you can do with the autograd function of PyTorch. So I will just disconnect from this notebook, and we will go through the other one. So this is the, now we go into the Gray-Scott solution using PyTorch. So this is based on the notebooks that you have for SciPy, for CuPy, and for the other NumPy libraries, actually, but we just modified them to use PyTorch instead of these libraries. Okay, so I will just choose the GPU as here, and I have my option with the profiler. So I can open both of them. Here I'm connected. So let's go through the exercise. So there is nothing to do from your side at the beginning of the exercise, okay? Because this is flawless. So it's something that you already saw. There will be two things to do here in the exercise. On the PyTorch is define the stencil. Okay, this is not that obvious because, as I said, we're working with tensors. We're not working with matrices. And also define the Laplacian for U and V. Okay, so in the beginning, I redid the notebook with the standard definition of the stencil. So all this you saw already. So Jean-Marc and Alice defined a loop by hand and the one using conv2d, okay? So we will compare both of them till here. Up. I validate all the functions in the notebook. Up. Make video. Here we define all the variables for Gray-Scott problem resolution with the number of steps, images, and all the stuff. Okay, so here we calculate the images. So this is gonna take some time because we're not using we're making the convolution by hand in the for loop, okay? So this is, if you go up, defined here. So this is using the CuPy function, and the other function here is a loop, okay? Where did I do it? It's still computing, so problem right now. So this is, yeah, the Laplacian loop by hand, okay? We're not using, we're making the convolution by hand here, okay? So this is rather slow, you see it. And on the other way, we can use the signal. So what I didn't say it in the beginning, but here we import the signal library from CuPy, okay, which has a 2D convolution function integrated with it. So the idea here is to compare when you do a loop by hand and we use an optimized loop from the signal library, okay? But all this normally you have already seen before. The idea here is to put through everything in the same notebook, okay? So I go back to my cell. Okay, so I have my image. So this is the initial image. And on collapse, actually, your image is here. You find them on the virtual machine, actually. Okay, so I close this. And now we do the same thing, okay, but using the convolution 2D from scikit-learn, so the signal library. And there you see that is rather fast. So we took almost like 16 seconds on the first one, and here it's like fraction of a second. So it's very useful. The lesson from this is very useful, actually, always to seek for optimized functions that are hardly coded in the libraries, then use it by, you can do it by yourself just to understand how things works, but sometimes you will not get the same optimization than libraries on which people worked a lot already before you. Okay, so this is a very obvious example of something that you do by hand and something that is optimized by the community, let's say. So here I calculate the time again. And so when you use the time function, it uses more time, but actually it's rather stable. If I click it again, we will be about, yeah, the 400, 450 milliseconds. So it's quite stable. So now we're going to try to make the same function, but with PyTorch, okay? So we have a convolution 2D available in PyTorch. Why do we have this? Because, as I said, PyTorch is deep learning library. In deep learning, you have two areas, image processing and language processing, okay? Language, you know it, it's the LLMs, OpenAI, etc. But you have also in PyTorch all the useful libraries to process images. And here in the Grayscale challenge, actually, we process actually the U and V field as an image. We can do that, okay? So we can use PyTorch libraries that are dedicated to image processing, try to gain some speed and see how it works, okay? So here I import PyTorch, okay? And I ask directly, is there a CUDA device that is available, okay? So now I'm on a T-form GPU. We can switch later on to A100 or whatever other machine to see if we get some speed. Okay, so check what are the current device. So this device is 0, so I can use the number for my variable attribution later on. I can get the device name, Tesla T4, as I said, and I can also get the memory that is allocated right now, which is 0 because I didn't send anything to the GPU yet, okay? The memory reserved, also 0, once again. I didn't allocate any tensor, nothing to the GPU, so the memory is still clean, okay? So here I create a tensor on the CPU, okay? I try to see on which device it is. So this is some parts of the previous exercise, flawless right now. Okay, we go on this. Okay, so the syntax, I get back to the syntaxes actually to send data from the CPU to the GPU. So you have two ways to do this. You say b2 CUDA, and you say b.CUDA, okay? So if you use the method to, actually, the CUDA method is more versatile in general than CUDA, okay? Is more specific because you can change, for example, here I gave you an example, so I will validate all this. Okay, here, for example, I changed the type of B directly when I move it from the CPU to the GPU, okay? So if you don't use the to method, actually, if you use only the CUDA method, actually, you cannot do this, okay? If you use the CUDA method, it means that you cannot change the type of your variable, okay? So the to method is more versatile because it gives you a lot more options, actually, when you transfer your data from the CPU to the GPU and to the GPU to the CPU, okay? So it's very important. You have some GPUs that are limited to 32. So you have a float 64 on your CPU. You can convert it to float 32 and lose precision by transferring directly by using the to method and specifying actually the type of the target type of your variable. Okay, so this is very important to understand the difference between .cuda or to-cuda. They're not the same. Okay, is this clear for everyone? Yeah. Let's go on. So this is, you already saw. Here I make some addition on CPU and GPU. So make sure what are your variable placed. So this is a mistake I did actually when I did the code. I did some additions and the variable were not at the same place. And actually, if I put B on the CPU and A is still on GPU, when I try to make the sum, actually, I have an error, of course. So really make attention to see where your variable are. Okay, here I recheck again my GPU. And here's the first exercise, actually. So you need to define or a stencil, which will define your Laplacian, actually. So we have the matrix, okay, that is here, okay. And I want you actually to go to the documentation of PyTorch, conv2d method, and try to define this tensor or matrix, okay? So I leave you 10 minutes to try to do this because it's not straightforward, okay? So for the people who have seen the solution, don't communicate it to the others. Let people read the documentation and understand actually really what is the difference here between a tensor and a tensor and a matrix, okay? So when we did it for scikit-learn, for scikit, it was a matrix, okay? A 3x3 matrix. When you do it here, it's a tensor. So the definition is different. You have to think about the dimensions you need to put your tensor. So what you will have here, you have a matrix, 3x3, close to a tensor, okay? So I leave you, let's say, 5 minutes or 10 minutes to do it, and I get back to you, okay? So did somebody find the solution or no? So the stencil is the same that you used before. So now you should know it by heart because you used it in many languages. So the stencil is still the 3x3 matrix. What we want to do here is to put it in the right tensor shape that allows the method conv2d to use it for the convolution in our case, okay? Does anybody have an idea, actually? No? Okay, so we go through the solution in that case. So here's the definition of the tensor we want. Okay, I will go back to the exercise. I will fill it up. Here we are. So what we do here, actually, so we create a tensor of 1, 1, 3, 3 dimensions. Okay, so I told you have a matrix that's 3x3. Your matrix is here, 3x3. So all the others, actually, if I create a tensor of 3x3, the conv2 method will give me an error because it expects a matrix convolution actually of 4 dimensions, not of 2 dimensions. So I'm okay with you that the image has 2 dimensions, but as we are in a library dedicated to image processing, actually images have channels by colors, and you have more than one dimension in it. Okay, so the expected tensor size in this case is 1 by 1 by 3 by 3, okay? And so if you define it this way, this works, okay? So this is what I'm doing in the second line. So here I fill it with zeros. And after I fill it, okay, so this is my tensor. And if you try to visualize it here, you have your 3 by 3 matrix, and you have here all the void dimensions that are in the brackets, okay? So if I do this, so this is okay. Now if I define my, so my Grayscale convolution 2D function extension PT for PyTorch, okay? This is okay. We go ahead. Okay, and now the second part of the exercise. So you have your stencil defined here. I want you to define the Laplacian of U, Laplacian of V here. So this is the second part of the exercise. So this is normally more easy than defining the tensor because we want over the tensor part. So I give you also, let's say, 5 minutes to do this for the people who want to do it. Okay, so we will go through the solution in that case. So this is the solution actually. If you see how the conv2d function is defined in PyTorch, actually you have this to add this stride equal 1 and padding equal 1 for the Laplacian definition. That's the only trick that is not obvious actually. Okay, so now if I validate here, my function will work. So into this step, actually, we have all our methods for PyTorch defined. So we have just to validate them. Okay. So same thing. So we had this issue for the remember for the stencil. You have also the same thing because you will multiply your tensor, which is a tensor with this a tensor for 4 dimensions with an image. So the image must be also 4 dimensions. So when you initialize your variables u0 and v0, you have to put these 3 dimensions in the beginning also. Okay, so this is really depending on the conv2d method in PyTorch. So you have also a conv3d method, and the same way you have to add a more dimension to it the same way. Okay, so this is really the tricky difference between matrices and tensors. That tensors have more dimensions that's not necessarily used, but you have to set them up actually just to make the computing work. So the other backflow of this is you need more memory for it. Okay. So tensor takes more memory than a matrix for the same object definition. Okay. So here the definition of the save image. Okay. The video making. So I let you go through this. This is very close to what you saw on CuPy actually. Okay. So here again we define our objects, the number of rows, the number of columns, the number of images what we need, the number of steps, the step, the derivation, and the coefficient actually. So this is these are the same variable that you had before. And here normally I should not. So I have an error. So I go back to my other notebook. Okay, so I have the U0 and V0 actually tensors that are defined. The save images function, definition of make video, .pt, all the variables, and then actually we compute. So here actually we're using the conv2d PyTorch library to make the image processing, the finite difference method actually to compute the image. So here we're computing the time. So we have our files that are saved in our results here. So we have all the images. And at the end, you have your video that is available, okay? So if I go back to my files, the video looks like this. So this is a good one. So it gives you this kind of, no, this is not the right parameters, sorry. So you can also tune the variables afterwards. If you change the variables, actually you see these patterns appearing, okay? So this is completely generated with the conv2d method of PyTorch, okay? So once again, on collapse, you have all your images, and actually you get the video is generated at the end, okay? So if you go back to the generate make video method here, actually, we have a method that is a video writer that creates the video from a set of images, okay? So this is not rather fast. There is another way to do it, which is using the video method from Torch Vision, which is quite faster, and it does it on the GPU. So here what we do, we generate the images on the GPU, we bring everything to the CPU, and then we generate the image, which is not quick. The best way to do it is to generate all the images on the GPU, to generate the video on the GPU using a dedicated library on the GPU, and then actually just bring back the video to the CPU, okay? So I'm not doing it the right way, but it's a good exercise for you actually to do it later on, okay? So some take-ons from the future, modify the image array to be handled on the GPU directly. So this is what I said. An idea from Jean-Marc, which is a very good idea, is to make a tensor that combines U and V. So U and V here are two separate tensors, okay? We define them as a different tensors. You can define a tensor that has two layers, U and V, in the same object. You see? And after, when you finish your computing, so it takes the same object, so it takes much less memory. And if you when you finish the computing, you take just the layer that interests you, here in our case, V, okay? So this is another way to do it, also another method to solve this. As I said, generate the video directly on the GPU. You can also use PyTorch JIT. I didn't try it myself, but it should be quicker. And now just I want to give you an insight of the PyTorch profiler. So there is you can use the CUDA profiler. You can also use the profiler provided with PyTorch. So you import it like this: pip install torch tb profiler. And you import profile, record function, and profile activity. So if I apply it, so I apply it only to the convolution function here, conv2d. Okay, so I click again, up. And when you get actually, it's an array of data. So what is interesting for you here is the time that you take to make the convolution 2D. And if you go to the CPU, to the GPU time, you get it here on average. So this is this line. Okay, so it's around 260 microseconds for a convolution, okay? So you can use this actually to profile your processing, changing your dimensions and everything, see the memory transfer, etc. Okay. So the only thing that it didn't succeed to do is to plot this actually on the tensor board. Well, tensor board is from TensorFlow. You have some tricks to do it to make it work with PyTorch. Till now it doesn't work, but it's also a good exercise for you. It's not flawless. You have to do a lot of things when you define actually your profile here to make it put the data, the log data, on the tensor board. So that's not easy, but you can already have a lot of insight of what is happening in your computing just with actually the output from the PyTorch profiler. Okay, any question? Is it clear for you about the difference between a tensor and an image actually? Yeah? I didn't see on Discord if there is any. Okay, so you have this this notebook also available on the repo. So this is this one, okay, but without the profiling. I have to put it updated with the profiling here. Okay, so there's all the working notebook with the correct tensor definition, the Laplacian definition, etc., available here. And you have, as I said, actually the Python script done by Jean-Marc and Alice actually is available here. You can just run it slowly, and actually it's in the right data type format to generate the video. And it should be very quick also. Okay, so if there is no question, thank you, and see you. And I plot this for the audience. Okay, so what you see actually is that CuPy, Torch, and JAX are not far away one from the other. Okay, so if you want to go through deep learning, maybe the good idea is to go through PyTorch or JAX. If you have some analytical function work, JAX is the way to go. I don't know if JAX is good for deep learning, for IA, Jean-Marc and Alice. I have no idea about that. For neural networks, JAX is okay for that. Deep learning, okay, so yes.
Is support for TPUs? No, pardon. Is support for TPUs expected soon in PyTorch? Do you know
TPUs,
the plans?
they've been working. The first merge request on it was like 11 or 10 months ago. So it's quite recent because Google didn't open it to the others before. So now, because PyTorch is a competitive, actually, competitor to TensorFlow, of course, you know it. So the integration was not flawless in the beginning in Colab, but now it works very well. I don't know what will be the time for TPU. I know I have it for my runtime, actually. I don't use it because I'm on PyTorch. If I want to switch to TPUs, I have to recode everything on TensorFlow. But it's doable. You can do the same thing we did in PyTorch and TensorFlow, by the way.
Yeah, okay.
For sure. I don't know if we can do it for Keras. I don't know if Keras have convolutions integrated. I know TensorFlow has it, but Keras, I'm not sure. But you can do the same job in TensorFlow, and then you access natively, you can access to the TPUs. Yes, and so it's much faster. So.
And from JAX?
For Jean-Marc, JAX, TPUs, probably because JAX is a Google library, I think.
Nice, yeah.
So in your case, maybe the way to go is more JAX. Yeah. TPUs are, quicker, faster than, we didn't make the tests, actually. That could be a good thing. So we have to import our JAX scripts on Colab. And here on the runtime, actually, I think we have the TPU runtime. I'm not sure. We will give it a check. Yes, the TPUs are available here. So if you take the JAX script, you import it here, and you select TPU. Normally, it should give you some insight on how fast it can go faster than the GPU. Really, something to do, I guess. If you want to do it, it's a good exercise.
Nice, thank you.
You're welcome. But I don't know, actually, in JAX, how you tag the TPU. I don't know if there is specific syntax to do that.
Yeah, we have to research.
Yeah. So.
And this CuNumeric, is it actually worth it to use it right now?
Me, no.
Considering the benchmark times.
Maybe Alice can answer this. The micro.
For CuPy numerics, I would say you can try with your program if it runs as is, because it's easy porting on GPU. But for the moment, it's still very young, so I would say in a few years maybe it will be better to use it. It will be worth the trouble of adapting your code, maybe if you have some adapting to make, removing some functions that are not supported. Yes, but I mean, you still have to maybe remove some functions if you use other functions than NumPy. it won't accept it, etc. So just maybe try it with your code to see.
What is the type of your code actually? It's more matrix multiplication, finite difference. What?
Not working anywhere right now.
Ah, okay. These actually the choices of this library are really like problem specific actually. Some libraries more be adapted to some other problems. So if you want to stick to matrix calculation, maybe CuPy is the way to go because it's easy, fast, and quick. If you have some function analysis, derivation, this kind of stuff, you can go with JAX or PyTorch. If you want to get access to TPUs, the answer is clear. It's JAX. So really depends on the hardware you want to target and the problem you want to solve. If you want to go to deep learning, in that case, Torch or JAX are the way to go. But Torch for deep learning, for now, PyTorch is much more mature actually than JAX. So, and it handles multiple GPUs and a lot of stuff behind the scenes. So it really depends on the problem you want to solve.
Yeah.
It's really problem specific. But it's good that you have the freedom also to choose. For me, PyTorch, I use it for this because I learned it before for deep learning. I didn't want to learn another library for another purpose. So the lazy way to do it actually is to use it for matrix calculation. That's it. That's it. There is no preference or no politics behind this. It's just more easy for me in this way. So, Pierre, I think we can end the session. Usually he ends the session, yeah? Yeah. So we have to invite him to end the session.
I mean, we still have 40 minutes, so if you have extra question or you
Yeah.
want to check other exercise or...
So if you want to redo the exercise of the convolution, go ahead. Reread the documentation is a nightmare, but it took me more than 40 minutes actually to find the solution. So anyway, we'll be around. If still some people have some questions, actually we can answer.